Good day, everyone, and welcome to the Engineer Construction Lecture Hub. Yeah, this is a live streaming. I want to talk about, the need for proper spacing of reinforcement in our beams. Although this has been discussed previously, but I deem it necessary to, you know, discuss it, to an extent in this live streaming for clarity. So if you're just joining us, this is a live streaming. Welcome especially to the Engineer Construction Lecture Hall. Let us kickstart. Let's start by, uh, getting to know what our beam stands for. Okay. Now, beams are horizontal members, in our buildings. Okay. Now, these beams are there to, transfer loads. Basically, their function is to transfer loads, and they have direct connection with the axial members, which are the columns. Okay. Now, these beams are regarded or referred to as flexural members. The reason is they transfer their loads via bending. Okay. Now, most times you see our buildings, especially those that have larger span, you see the depth of beam having a corresponding function, okay, with respect to the span. All right. So today basically we want to look at those are the proper spacing of our reinforcement, the essence of proper spacing of our reinforcements. Okay. Now, reinforcements are there in the beam basically to take care of shear stresses. Okay, shear stresses are generated more close to the what's it called, the supports. Okay, now it is shown that beams usually experience maximum shear force close to the support. Okay, so it is the stirrups that helps to take care of those stresses, those shear stresses that are generated at close to the support along the beam. Okay, along a section of the beam, and usually those sections are referred to as the tension zone. Okay, the tension zone. These are the areas, critical areas along the section of a beam that experiences, shear stresses more. Okay, and those areas are found close to the support. Okay, so normally our stirrups are there to take care of shear, to enhance shear stability. Okay, it is there to enhance shear stability. Now, most times you see that when we space our stirrups along the main bar, okay, of that beam, you discover that the stirrups is there to keep the main bars in position. Okay, they are there. One of the reasons for having stirrups in our beams is to keep the main bars in position. All right, giving the required spacings. All right, so then another thing that the stirrup does is that it enhances shear stability. Okay, it enhances shear stability. Like I said, cracks are experienced more in our beams along the section of that beam that is close to the support. Okay, so that is why it is important to ensure that the spacing of our stirrups close to the support are considerate. Okay, compared to the mid-span of our beams, because maximum moment is felt at the midspan, and the stirrups are there to take care of shear forces, all right, while the main bars is there to take care of the maximum bending moment, which is usually the sagging moment, and is experienced at the midspan of our beams. Okay, you're welcome. If you're just joining us, we are looking at spacing of stirrups in ROC beams. Okay, so now, like I said, the stirrups are there to take care of, to ensure shear stability. Then, to an extent, they also helps to provide resistance to flexural, or they also contribute to flexural stability. The reason is that they help to keep the main bars in position. They help to keep the main bars to maintain that required depth that will enhance flexural stability. Now, flexural stability, I'm talking about the bending tendency of our beams. Okay, so it is the stirrups that keeps the main bars in position. Okay, because for our beams to be able to perform, okay, optimally, with respect to the span, is a function of the depth of that beam. Okay, so when you have situations where you have larger span of beams, okay, like 7.5 meters, 7 meters, 7.5 meters, thereabout, okay, you discover that the depth, the stirrup, the depth that stirrups make, okay, that is what gives the main bar that ability to be able to take care of, bending effect in that beam, which is the flexural aspect. So that is why stirrups also helps to maintain flexural stability in our beams. But basically, the main function, okay, of stirrups in our beam is to take care of shear stresses, which in other words is to maintain shear stability in our beams. Okay, then also another perspective, another aspect I want us to look at is the area of load transfer system. Okay, load transfer system is another aspect very important when it has to do with our beams, because our beams usually carries our slabs, and they are hinged at supports, which are axial members, are columns. Okay, so they are more of an intermediary. Okay, so they receive the loads from the beam, from the slab, and now they will split it both ways, okay, to the columns, to the supports. All right, now for it to perform its function in the load transfer system, the stirrups plays a very important role. Okay, the stirrup plays a very important role. So the spacing of our stirrups is very, very important, because it is what also gives the beam that internal capacity, that internal strength to be able to, transfer load effectively without any form of excessive deformation. All right, so it is important that we look at our spacings critically. Now, most times, ideally, beams, spacings of our stirrups close to support should be closer, okay, compared to the sections at the mid-span, because at the mid-span, shear force is zero. Okay, there is no shear force experienced at the mid-span of our beams. Okay, but their maximum are close to the support. Okay, so that is why in an ideal setting, the spacing of our stirrups should be closer. Spacing of our stirrups for our beams should be closer at the section that is near the support, while at mid-span it should, it should maintain it's the original spacing. All right, if it is 225 millimeter spacing, okay, if it's 300 millimeter spacing, as the case may be, because the spacing of our stirrups also is a function of the main bar. Okay, the diameter of our main bar also determines the spacing of our stirrup. So you have to take note of that, because, for example, if you're using if you're using main bar of 16 mm, okay, and also 12 mm, you discover that the spacing as well will differ. Okay, will differ for economical consideration. All right, then also, like I said, shear force is maximum close to the support, okay, but shear force is zero at the midspan. Okay, so what we should be considering more at the midspan is the sagging moment, okay, which our main bar, okay, is there to take care of that sagging effect. Okay, you know, we have the bottom bar and the top bar, okay, for our beams. Now the bottom bar is designed, is the main bar, okay, that's the main bar, so it takes care of tensile stresses. Usually it is known as the tension zone, because in our beams, where our beams are splitted into two, okay, the lower part is referred to as the tension zone, while the upper part is referred to as the compression zone. So when our beam is loaded, there is usually this situation that takes place where the bottom part of that beam will be tensioned, okay, will be tensioned, and that tension will lead to a kind of elongation, and that elongation can cause an internal distortion, which will lead to cracking, okay, crack formation. All right, and when there is no reinforcement, you see that that concrete will not have that tensile strength to be able to sustain that beam. Okay, so that is why we normally provide reinforcement at the bottom, which is usually the main bars. It's usually positioned at the bottom of our beams. Now, in most cases where that stresses is excessive, okay, and with the compression effect at the top is more, that means we have to also design for compressional reinforcement bars, reinforcement bars that will take care of stresses that will be experienced at the compression zone. So you now have reinforcement at the bottom, reinforcement at the top. But in a case where that effect is not much, okay, is negligible, that means you have to provide nominal bars at the top. But generally, these bars are to be kept in position by the use of our stirrups. Okay, our stirrups is there to keep these bars in position, okay, to keep the bottom bar in position, to also keep the top, which is the compressional reinforcement, in position as well. Okay, so, and with the right spacing. So like I said earlier, we should understand that in the load transfer system, these stirrups also contribute in enhancing lateral stability, okay, because these beams are horizontal members. All right, now if these stirrups are spaced, okay, if the spaces are maintained uniformly, you will see that it will not perform compared to when the reinforcement close to the support, that is close to the columns, are closely spaced, okay, because the stresses, the shear stresses is more at that section of our beams both ends. Okay, usually those are the tension areas, okay, where we experience tensile stresses, which will manifest in the form of cracks. And being a member that transfers load via bending, it is important this flexural member maintains a good state, okay, for it to be able to transfer load effectively. Okay, so spacings of our member of our beams is very, very essential. Is very, very important. Then another thing I want us to also to look at also is the bend. Okay, the bend we give to our stirrups also very, very important, as well as the placement. Okay, we place them, we alternate them. Okay, what I mean alternating, the area where you have your bend, okay, usually 135 degree bend, okay, where you have this bend, you alternate them. When you place one this way, okay, maybe you place it this way, all right, the other one should go this way, all right. So that is how you are expected to alternate these stirrups. That will give that stirrup the required, that will give the beam the required rigidity, all right. Then in the aspect of the bend I've talked about, you must maintain a 135 degree bend, okay, because there are some areas, some sites you go, you see them doing 90 degree bend. Now 90 degree bend is not ideal, okay, for flexural members. The reason is that as these beams transfer their load via bending, once the load exceeds the internal capacity of that beam, definitely it will lead to crack formation. It will lead to crack formation. Now, when you have a 90 degree bend, okay, of that stirrup, you see that when the stresses over exceeds the internal resistance of that beam, you see that 90 degree bend will give way, okay, it will give way. And once it gives way, the main bar will not have that retention anymore, okay, that ability to transfer that load will not be there anymore, okay. And that is a situation where that beam will be said to have failed, okay, because once a beam cannot transfer, okay, load, all right, it means that it is defective. And being defective means that beam has failed, all right. So in most cases, usually retrofitting can remedy that situation, but that is in the aspect of trying to sustain that beam. But at the inception, there is need to do the needful, okay, so that our beams can be able to perform optimally. So it is important that we maintain 135 degrees bend for our stirrups, okay. Then also in the area of placement, we should also alternate them, okay, because alternating these stirrups will give that beam the required ability to transfer load, okay. Now there is another aspect I want us to look at also, the area of deflection. In our design, when we design for our beams, we check for deflection, okay. Now in terms of serviceability, now deflection in this regards now have impact on the appearance of that beam, okay. For example, when you have a very large span of beam, okay, that is not supported by a wall, all right, now, and that beam is to carry a slab. Now it is important that we look at the depth of that beam critically, okay. And what gives that depth for our beam is the stirrups. Okay, it is the stirrups that helps us that regulates the depth of our beam. Okay, so whatever depth that we want to give to our beam is dependent on the size of the reinforcement we give to that beam. All right, now that depth also have a direct function with the spacing of the stirrups. Okay, then also the diameter of the stirrup, we use 8 mm diameter bar, usually mild steel reinforcement, mild steel bars, okay, for our stirrups. Now the diameter is also a function of the spacing. All right, it's also a function of the spacing. So the load now, generally in our design, once you have designed for that beam, okay, you must also design for the shear. You have to look for the shear stresses. You have to estimate the shear stresses that beam will be subjected to. Okay, now that the shear stresses is what will enable us to come up with the size of stirrups to be used for that beam. So you can see that structural design is very, very important when it comes to construction, because in the course of design there are parameters, okay, provided in the code that was put into that was a kind of analyzed, okay, before designing. All right, so you see that these parameters are what translates to what we have at site. Okay, so that is why it's important, whatever that was used or whatever the outcome of our design provides, we must follow that provision in the implementation, that is in the execution of that construction work. That is the only way we can give our structure that functionality. All right, then in the area, because most times you see that when we want to look at our structure critically, we must ensure that every component of our structure performs optimally. Okay, both the horizontally positioned, the vertically, the inclined components in our buildings. These components are interconnected. Okay, and that will give rise to being a monolithic structure. Okay, so these beams should have sufficient development length in our column, because when our columns are vertically positioned, the top bars, okay, are supposed to maintain certain length of bend, okay, which goes across the transversing beams. Okay, because when you have a column, usually you have your primary beams and your secondary beams. Okay, most times you see that our secondary beams are hinged to our primary beams. Basically is to break the span. Where we have light spans, we tend to break those spans by having secondary beams. Okay, so these secondary beams most times are being hinged to the primary beams. Now, when they are hinged to the primary beams, it is expected that the top bar should have development length, okay, as well as the one below, the main bar, should also have the development length, a sufficient development length that will create proper anchorage. Okay, because once concrete comes in, concrete helps to now bind this reinforcement, creating that binding effect that will not give room for any internal slipping of this reinforcement. Okay, so once we create that anchorage in our beams, then having our stirrups, close to those supports, you see that beam will perform optimally. Okay, now also when you have two beams, okay, running to a column, okay, you have the one on the other side. It is important to have a lateral a lateral tie that will hold these beams at that junction. There should be a lateral tie that will bind them together. Okay, that will help to improve the performance of those beams with respect to their spanning directions. All right, so our stirrups plays a very important role in our beams. All right, so I deem it necessary to bring this our way so we can be able to understand the need for spacing of our stirrups. So please, if you're just joining us, we are looking at proper spacing, of the need for proper spacing of our stirrups in our beams. And we've talked about that our stirrups, the spacing of our stirrups helps to keep the main bars in their right position. Okay, keeping them in their right position will enhance shear stability. That is, having the stirrups closely spaced at the section of the beam that is close to the columns. All right, both ends. Then when we talk about flexural stability, is when main bars that are there to take care of the sagging moment, are kept in place by the help of our stirrups. Okay, so you see that the presence of stirrups in our beams enhances or maintains shear stability and also flexural stability. But basically our stirrups takes care of shear stresses. Okay, they takes care of shear stresses because in our beams, being an horizontal member, you see that the weaker or the side that is weak more is the side that is close, or the side that is prone to crack formation is that section of the beam that is close to the support. All right, that is the section at both ends. Those are the sections. That is why those sections are referred to as tension zone. That is horizontally. All right, they are tension zones. So that is why it is important we do close spacings, at those sections. Then maintain, spacings that are more than those spacings close to the midspan, because at the midspan, shear stresses are less. Okay, shear forces is 0 at the midspan. Okay, so we must understand this the dynamics here, because at that point is usually a point we refer to as point of contraflexion. Okay, that is where there is a change of moments. Okay, positive and negative moments. All right, so these are what are associated to beams. All right, so I want us to understand basically that the spacing of our stirrups in our beams is very, very important. It's absolutely essential. Okay, because once you wrongly space your stirrups, it will affect that beam. You see that most times deflection is also associated to the spacings of our stirrups in our beams. All right, then also when you're spacing your stirrup, they should be vertically positioned. Okay, not in a slanted format. Okay, because when you slant it, it means that you are limiting that section of that beam. Okay, but if it's properly vertically positioned, you see that it will give that beam the required depth to be able to, transfer load effectively. All right. So if there are questions as regards to the topic of discourse, you can send them across for further clarification. All right. So thank you so much for every one of you that has been online. Thank you so much for your time. Please endeavor to stick or stay connected to Bengineer Construction Lecture Hub. This is a platform where updates as regards to construction will be coming your way. Thank you so much for your time, and do have a wonderful day. Thank you, and bye. Bye. Yeah. See you in the next. All right. See you. Bye.